Okay, I think it's a particular pleasure to come here at the first Human Brain Project student conference. For one thing, I'm sort of like many scientists, I'm involved in the Human Brain Project. But also, I think that this talk is very much sort of aimed at people like you, meaning at the start of your scientific careers, and it's very much like a bird's eye perspective kind of talk. So neuroscience with both hands, bridging scales with mathematics. So it's really about sort of like how best to do neuroscience. And I used to do in the old days. I'm trained as a physicist. I used to do semiconductor physics. That physics has to do with how you make materials for making computers. And then I took a PhD in semiconductor physics, and I was a postdoc also in semiconductor physics. And then I got introduced to neuroscience, and then I switched to computational neuroscience. And it's this thing of changing field from semiconductor physics to neuroscience was actually a very interesting experience. And it's a little bit like the first time you leave your country. You learn a lot about the country you come to, but also about your own country, that there are different ways to do things. And one thing I realized after spending some years now, the last 20 years of my science career in neuroscience, is that it's really done in a very different way than like in the physics. And science is done differently in neuroscience than in the semiconductor physics where I sort of grew up. So that's really the overall perspective here. So I don't know if any of you recognize this guy. He's obviously sort of famous in Norway, at least in Norwegian science. He's on the stamp. So this is this guy, mathematician Abel. So he's maybe the most well-known Norwegian mathematician. What is most important here is that he died only 27 years old, very young. And when you read his, I read his biography, and when he died, he died on this farm outside, in Norway, and he was so upset about the medical doctors. So why can't he die of tuberculosis? Why can't they fix this silly thing? How stupid are these doctors? Why can't they And of course now in the Western world they don't die of tuberculosis anymore. But there are other things that, if you come from the doctor with like a serious diagnosis regarding your brain, like it could be like, for example, dementia, it could be older people, or maybe like schizophrenia, or like some of these serious psychiatric disorders, then it's very little that we have to offer, simply like tuberculosis in 1827. So why is that? Why are we doing so poorly when it comes to the brain? And of course, it's not that there's lack of resources put in, or at least it's been a lot of brain research going on, and it's also that these diseases, that brain diseases, for example, dementia, and also schizophrenia, which then afflicts a lot of not only patients but also families. They are in the rich part of the world, so it's not like the pharmaceutical company that can come up with drugs will make a lot of money. It's not a third world disease, so the patients have money. So it's just that we're doing, at least we haven't been successful. So then we should sort of start asking ourselves: are we doing science the right way? Is it? At least it's something that should be considered. And then you can point maybe to, and then maybe people say, well, it's very hard. The brain is very hard to understand because they have all these different scales. And that's true. We have all these different scales, like spatial scales, all the way from proteins up to like the body, and also time scales, from the time scales of molecular interactions all the way up to the lifespan of man. So this is sort of complicated. It's like a problem that is. You have to understand things at different scales and hook up these scales. But, so this is true. But we have dealt, we meaning mankind, or humankind, maybe we should say that, like for example weather prediction. I think there's an interesting analogy between, I would say, weather prediction, the problem of weather prediction, actually understanding how the brain works. This weather prediction involves a lot of, there was this I'm showing a lot of famous Norwegians here. This is another famous Norwegian. So he made it all the way to the tail fin on the Norwegian. Actually, Norwegian are flying so much now that you don't have to be a very famous Norwegian in order to get to them. So it's almost like you're open for like any kind of celebrity will soon make it to there. They're flying all over the world. Anyway, but this guy really deserved to be on the tail fin. So Norway has strong traditions in meteorology. And he said already in 1900 that the weather prediction is a mathematical problem. And what he said was that the basic laws of physics for how weather develops is understood. We know the basic laws of sort of how the wind and like the humidity and all these basic physical processes, and we know how to describe them mathematically. So if you know the weather now, meaning that you know all these physical variables now, you should be able to compute the weather in the future. Of course, this at the time was sort of like doing this in practice was very difficult because they didn't have computers at the time. And of course, then you can also say, well, this is impossible because you have all these scales, right? And here's just like the scales of like weather predictions, all the way from I guess it's 10 meters turbulence, and all the way up to computing the weather, like on the whole globe. So I have all these scales, physical processes that has to be dealt with, all this data that has to be assimilated and so on. But now it works. So the first weather forecast from mathematical models came in 1954. Of course, that was just with the start of computers. I don't know how good they were, but now all weather forecasts on that we are presented are computed. It's just a fantastic thing, right? That you can actually, everything is just computed. So now, for example, this is sort of like just something I downloaded from a smartphone. This is a weather prediction from Vienna. I'm not quite sure how good it was, but according to, a few days ago, they predicted to be 0 degrees. But at least statistically, if you sort of look at this has gradually improved. So now the weather, this numerical weather forecast predicts 1 day better every decade, meaning that the accuracy of the 6-day forecast today is as good as the 5-day forecast 10 years ago. And it's not like this was sort of like this was done. So it's been this gradual improvement from getting this, starting to do this, and then it's improved in supercomputers, and it's also improved in way to do sort of like statistical modeling modeling how to deal with data, integrate data, and so on. So this has been done by a community. It hasn't been done by, it's not like one very famous meteorologist that everybody knows the name of. We don't have like the Stephen Hawking of meteorology. And it's really the community of meteorologists and all these like supercomputer centers around the world which has made this possible. So I think there's a lot to learn here about sort of how to if you want to build this kind of model, you need to be a community. So there's actually, if you want to this interesting review paper, The Quiet Revolution of Numerical Weather Prediction, that was sort of came out in Nature, maybe it was like a couple of years ago or something. So this tells how this has been achieved, and I think this has really been one of the, I would say, like one of the most impressive achievements of science in the world. Actually, this how we can sort of do this very accurate now numerical weather prediction. Another example, which is sort of closer to home, maybe, or at least everybody has one, is the smartphone. To think of that also involves a lot of scales, and that is something that is man-made, so it's slightly different in that sense. So if you look at all these levels in the brain, atom, molecule, molecular network, neuron, neural circuit, brain, that's like one way to set it up at least. We can so actually make analogies to these different levels in the smartphone, because atoms are atoms, and then you have like semiconductor crystals, and then you have tailored materials. This is what I worked on before I got into neuroscience. By the way, it's called these heterostructures. Really cool, but not as cool as the brain, but sort of but or sort of cool. And then the transistor, then analogous to neuron, and then all the way up here. And then, and so this has sort of this thing has not, it's not like one person understands all these levels. Typically, each of the people, I mean, people working on this, they're working on some of these levels, but they've been able to communicate between the people working at the different levels. And the language which has been key to do this is mathematics. That's sort of it's really the language of mathematics, typically then, which has been like the key of engineering and like physics, I would say, which has made this kind of scale bridging possible. Also, if you look at the program, the programming things, it's also multi-scale because we program with our finger, and then we don't have to worry about how this is sort of translated down to the transistor level in the hardware and how it switches, I said. And also the people who sort of computed this, your app, doesn't know it either. He or she just learns sort of like some other kind of meta language, which is then, and then below there you have another more like maybe like 2-3 levels until you get down to like a machine language. So, but the key thing again is that you need a precise language. So, and then we can ask, why do we I guess most of us, or us, you, at least many of you, have learned about mathematical models. But still, it's important to remind ourselves, why do we make mathematical models of things? And the key thing is really that mathematical models give more precise statements about nature than models in words. It's not that mathematical models are correct by necessarily. I mean, if you just come up with a random mathematical model, probably doesn't describe anything of nature. But the point is that the wording is such that it's very precise. So you can test your model. Test your model against experiments or observations, and then more easily find out whether the model is good or not. So that is really the key thing. Mathematical models give quantitative predictions, how much, while models in words give more like qualitative predictions, in what direction. So just as an example of this, a very simple illustration, or at least like a very, one of the first, at least an old illustration, where we look at dropping rocks into the sea. Not the most interesting experiment maybe, but that is something I guess we've all done at some point. Maybe not sort of like measuring everything so accurately, but at least we have observed what happens. So one thing you can, if you make this, start dropping out different rocks with different masses into the sea, then we can sort of make some observations. For example, see that we find that all rocks use the same time to fall into water when dropped from the same height h. So meaning that whether it's a big rock or a small rock, they fall in the ocean at the same time. So this is a qualitative observation. And then if you do the mathematical model, which is in this case is Newton's law, then you actually find that the time it takes is the square root of the 2 times the acceleration of gravity and h, the height, but for all masses. So the masses doesn't go in here. So this sort of explains why the mass or the size of the rock doesn't matter. But then you have another observation maybe, saying that you can see that if you measure the speed that the rock has when it hits the water, then, and as a function of height, you'll see that the larger the height, the larger the speed when the rock hits water. So this is a qualitative observation, which is true. But this is still not as precise as what comes out of Newton's law, which says that the velocity goes like the square root of the height. It doesn't go like linear with the height or the square of the height. It really goes as a square root of the height. So that means that if you then measure this precisely, and you find that it sort of is, then you can sort of test precisely whether it really follows this or not. So it's much easier to find out whether this prediction is correct, or if this law is correct, then this is a lot of sort of formulas or a lot of theories are compatible with this. And then also this law also illustrates this, how you can bridging scales with Newton's laws. This is Newton watching an apple and finding this law describing how the apple falls to the ground. And then he also used the same law to predict both the the planetary orbits and also like this flow of like ebb and tide. So we had this same mathematical law that sort of actually bridged these scales and showed how like phenomena on one scale was related to the other. So these are all this. So what's the take-home message if we go back to this question of how to do neuroscience? Well, I think the main thing that we see from like the successes of like metrology or making smartphones or like understanding sort of like falling objects is that there's been this tight interaction between experimentalists and modelers. So it's what's sort of been like this two-handed science. And so this is sort of what I'm arguing here also, that you neuroscience with both hands. We need to find a way to have an effective collaboration between experiments and modelers. And this is not, there are some organizational limitations or challenges. And that is when you study physics or engineering, typically you take a master's or a bachelor and maybe a master, then the first 5 years are the same whether you go do experiments or modeling. So the people are like, the students are socialized into sort of learning each other's language. Everybody does some experiments, everybody does some modeling, and then maybe if you stay in science or maybe going into a company, then you specialize into doing experiments or modeling. But these 5 years together, I think, is really important for sort of to foster this kind of collaboration, and that is something which is currently lacking in neuroscience, right? Where the people who do experiments typically have a background in biology or medicine, and the people who do modeling maybe have a background in physics or engineering or computer science. So then we try to meet after 5 years, sort of like separate education, and try to meet like venues like this, I guess. And it's it's quite challenging. For one thing, we need to sort of be, well, I mean, one thing you have to be open to try to interact with people with a different background, but it's also the language is not the same. It's all kind of challenges. So I would hope maybe that gradually we'll start getting neuroscience programs, for example, where people do modeling and experimentalists really experiments sort of actually do the same thing, just starting after high school. So neuroscience with both hands. So what are the challenges? Well, one good thing is that we sort of know if you have the this is like the different scales. We have good mathematical descriptions of how the system behaves at different levels of detail. So, for example, at the atom molecule level, you have the quantum mechanical Schrödinger equation. Maybe at the neuron, we have this cable equation, and we have also different kinds of models. So at different levels. So we have developed these different models at different levels, but we don't really know how to hook them up together. And this is not something which, because one thing is sort of if you go back to Newton, actually, Newton did many cool things, obviously, but one thing he had this idea of the law of attraction, this law of the gravitational force, that two masses actually sort of attract each other. So that was always his basic idea, and then he needed to test how can I check whether this idea is correct or wrong. Well, and then he needed. He needed this like F equals ma, this mass law. So that's fine. But then next you need to know sort of how do you, given that you have these two masses that follow Newton's law, and then also have this particular attraction law in proportion to the square distance. Then what? Well, then you need mathematics actually to compute. So what happens with this law if you're around the sun? Or what happens with this law if you're falling from a tree? What happens with this law in different circumstances? And that's when he actually needed to develop his own mathematics, calculus. So, so without that, he wouldn't be able to check whether his prediction or his guess about the gravitational law was right or wrong. And that's very much the same here in when it comes to the brain. It's very different. If I have some idea that, say, on a molecular level, I think this molecule is really important for how sort of a brain circuit works. So how do you test that? Well, there's no way to test it really without, or you would like to be able to put this into a model and see what are the consequences, and then check whether that actually pans out or not. So in some sense, we need to do the same thing as the analogous thing to develop in calculus. I mean, we need to have developed this computing infrastructure to be able to test to do this mathematical, sort of like a mathematical observatory to test your hypothesis. So there are several projects. Of course, our project, favorite project, this is Human Brain Project in Europe. But there's also other large-scale projects, both in the US, the Brain Project that Obama started. And it wasn't nice when Obama was the president, by the way. It's only a few weeks ago. It feels like an eternity, but anyway. And then we have this Mindscope project, which at the Allen Institute of Brain Science, which is also this thing of trying to bridge scales. Yeah. So now I'm going to start looking sort of how to do this in practice with mathematics. So we start in the middle here with a neuron, which is in some sense is like I think maybe if you should send one like text message to a foreign civilization about how does the brain work, I would say, well, they have this thing called neuron, that 100 billion neurons who send signals to each other inside our head, and somehow that make us think. That's sort of like at least the first really compact version. So we need to understand a neuron. We need to have a good mathematical description of neuron. Here's a beautiful neuron, which is green stained with green. So you have like the soma and dendrites and also this little thing called axon, and that's you know why we can see that it's an axon. Yeah, I don't know. Well, it's actually very thin, and why does thin things correspond to? I don't really know. I just learned it from a neurobiologist actually. That somehow it's always the thinnest thing there is the axon. Anyway, but the cool thing in terms of making a model is that we know how a single neuron processes information. We have a biophysical understanding of how a single neuron actually gets input from others. You get these signals in at your dendrite shown up here, and they spread down electrically down to the soma, and if there's enough current coming in over a time window, you generate this action potential which moves from itself down the axon, the thin axon, and then to the synapse, where it sort of leads to these little molecules drifting over to the receiving neuron, and the whole cycle can start again. So, but the key thing is that we have good mathematical descriptions available for all processes. And this really started with the work of Hodgkin-Huxley. Maybe many of you have probably know a little bit about that. So they were able to find this squid that had this very thick axon. So they were able to make this mathematical model for how a signal and an action potential is generated in this like thin tube axon, and also how it propagates. So I'm not going to go into the equations here, but it was really the key idea is that you had essentially these cable properties of the neuron keeping track of all the currents, and then they found that there were two key currents going through the membrane. One like by sodium, one by potassium, and they were sort of like independently regulated. So and this they could find out because this tube is so thick that you can actually start changing the potassium concentration, sodium concentration, and really. So it really was this fantastic gift from nature to have this really thick axon. So they came up with this model, and from that they could essentially fit all the model parameters from one set of experiments, and then predict, then with the fitted model, this propagation of action potential. The model generated action potential just like the experiment, and the shape looked nice, and the velocity was almost the same, like 21.2 meters per second for the experiment and almost 19 for the theory. So this is one of the biggest successes of not only neuroscience or computational neuroscience, but also computational biology altogether. So what is the take-home? I mean, this was sort of the impressive thing, obviously, but there's also some principal things here that should be noted, because this model was bridging scales, because it really was a model for how the neuron behaved, and then it needed some input from what's really happening at the molecular network, at least molecules going to the ion channels, which are made out of like these protein molecules going up and down through the membrane, making this tunnel. So now, so they just from this modeling, they hypothesized that there must be these ion channels, and they have now been discovered later. And now we can actually, it's like a separate modeling project to understand why these particular ion channels, and also with this, because Hodgkin and Huxley had to fit these G's to experiments, but now, like a separate project is sort of to understand where does these G's come from. Then you can sort of start at a lower level and make like physics-based models and understand and sort of understand where the Hodgkin-Huxley ion channels comes from. So this also was like one step in this like scale hierarchy. So based on this Hodgkin-Huxley model, we have now, this has been generalized so that we can now model the entire neuron, which is called compartmental modeling. So you take a neuron and divide it up into small pieces, and then you keep track of all currents. The pieces are called compartments, and then you keep track of all currents going in and out of each compartment. Essentially, it's just like it's essentially Kirchhoff's current law from electrical circuits, and then you get one equation like this for each compartment, so that if you then know, if you specify all the parameters for all current terms in all segments, it's actually quite straightforward to do this modeling. And there's like tailor-made free mathematical simulators which are available for this. And we use neuron, for example, and this is an animation that Espen Hagen in our group made, just showing the membrane potential. I guess it's 4 or 5 neurons here, who then receive some input. So you see it's blinking, and that's every time they're firing these action potentials. Blue means that it's like around resting level, and then it gets up to and you can see every time it blinks, it gets up to higher level. So the thing is that we sort of can like master, so we can make this like biophysically detailed models of neurons and look at the consequences. So a next step then is trying to go from the neuron and upwards to the circuit. So, for example, if we then, for example, then this is an image of like these are from the barrel cortex, and there's like several projects going on trying to understand this circuits of such neurons, and probably many of you have heard about the Blue Brain project, which is sort of like Blue Brain is sort of part of that, is sort of going into the human brain project, where they had like done these biophysically detailed models with I think with like 35,000 neurons or something like that. But that's not the only way to I mean, there's not the only way to study these circuits. And what we have done is also to look at to look at circuits with more simplified neural models. And it's not only, there's like two reasons for doing that. One is that it doesn't take so much computer time to simulate a simpler neuron than a more biophysically detailed neuron. So then you can simulate larger networks. But also, it's very difficult to know the parameters of all the parameters of these biophysically detailed models. So sometimes it's actually easier to fit the parameters of a simpler model, because then you can sort of choose the parameters to give it a particular function. But it's not like an either or. I think both biophysically detailed and simpler neural models have their pros and cons. But what you can do is sort of typically what you always do is to remove the axon, because that's the propagation of action potential. It's sort of like a little bit what's it called? It's like ironic, because the only thing we really know how to compute, almost not all, but at least the Hodgkin-Huxley computation of how an action potential propagates down the axon, that is, or it's moving at the same speed, so you don't really need to do it anymore. So the only thing we really know how to do, we don't do, because it's just a waste of computer power in some sense. So what we really compute is just the time the action potential is generated, and then we just time it, how long time it takes to get it to the receiving neuron. But then we can start making simplified versions of it and simplify the dendritic structure and maybe reduce it to a single point. And that's not as dramatic as it seems, meaning that it doesn't have to be circular in order for this to be a good approximation. What it means is that if you have thick dendrites, then the membrane potential, the potential inside the cell is not going to be very much. And that's really the assumption, not that it looks spherical. So then we have this famous, or at least famous among modelers, and very well studied integrated fire model neuron, and where we actually we sort of look at we have this very simple equation for how inputs into a neuron is summed up and how that changes the membrane potential. And if the membrane potential then reaches a preset threshold, then we put in, like in this case, E threshold, we put in a spike by hand. So this is what is shown here, spike. And then we reset it, and then the process goes on again. So that means that it's you only need to compute are this like one equation for each neuron, and then you just put in the spikes by hand. Now I want to take a little bit sort of like a commercial break, or not a commercial break, but it's a little break because we have this really cool program, Neuronify, that some are like PhD students in our group in Oslo have made. They were very much into this making apps and stuff before they got interested in neuroscience. So now they have combined it to make this this new app, or it's a new program, Neuronify, which is available at any smartphone. It's like the iPhone and whatever for the Androids and everything. So you can just download it. It's free. So there you can actually build your own little circuit by like pushing like just plug and play. So here's an example. This is the menu, and then you can sort of so this is like where you make a neuron. So you put in this is like with integrated fire neurons, 2 integrated fire neurons, and then we need to make some action. We need to drive it with something. So we drive in a DC current source, and then a voltmeter, and then you have to hook it up to get. So now this DC current source drives this one neuron. So you see it spikes now. It blinks. And then you hook it up to, well, it's even feedback, really cool. So then you can sort of, so then you hook it up to these voltmeters. So then you can see how this, so you can play like this, just making, and there's another like more advanced circuit doing something, I don't really know what, but you can also, but it blinks a lot. Yeah, it looks cool. Yeah, and it also you can actually also there's like this. You can also hook it up to your camera, so you can have this like visual input to your circuit, and also push all kinds of cool things. So this is the main goal of this is really to use in teaching. So you have this idea that this is a way like people can make their own circuits and sort of play with it, and of course if you're bored at the airport, why not make a really clever circuit doing something with Neuronify. Anyway, so this is now. That was the commercial break, and so now with the integrated fire neuron, we can now make circuits. So this is a model that because most of the studies of networks has been really on more like generic properties of networks. What kind of dynamics can you get if you hook up two populations to each other and so on? But it hasn't really been trying to mimic a specific biological system. And this is like a first candidate model, which is aimed to mimic how like 1 square millimeter of cat visual cortex, so that's about 80,000 integrated fire neurons, has like 4 layers, 2 neuron population in each layer, so it's altogether 8 population. And then we have this, it's hooked up with these synaptic connection rules, which are taken from experiments. And this was published then by 2 years ago in Cerebral Cortex. And it's run in Nest, and I think that the main thing here really is that, I think this is like it's an okay model, but it's not. It's certainly just like a start model. But the thing is that this is not publicly available. Everybody can just take this down and change the parameters and come up with ideas, good or bad, and see what happens, and then actually get feedback on their own computer in normal time. So this is like a way to, and what is important about that is then if you have an idea about what the circuit does, then you should formulate it. You can formulate it precisely in terms of your hypothesis is formulated in the models you choose and the connection rules, which are then precisely made in mathematics. So it's like a precise way to formulate your hypothesis, and then you can look at the consequences. So this is just an example of this Potjans Diesmann model that computes spikes, and in this case it's actually thalamic input shown here happening at time 900, and so it's going to loop here. So what we can see here is then we can follow how actually the first excitation layer 4. This is this 80,000 neurons, but this just shows like a subset of them, so that it's that we can get an idea about the structure. So this is a model that produces then spikes, which are then, in some aspects reproduces what is seen in the experiments. But now, so typical network models, they compute spikes, action potentials. But this is not what we measure, or not the only thing we measure anymore. So now there's all these new measures of cortical activity. So which is shown, this is like a piece of cortex, just shown schematically. So the traditional way to measure activity is to measure spikes by putting down a sharp electrode. And then you can measure spikes from individual neurons or a handful of neurons. And you can actually, if you have a really, really good, you can then have a very cool electrode, sharp or patch electrode. You can measure the membrane potential. But then you have a separate type of electrode, which is used a lot now, these multi-electrodes, where you have many contacts. Like in this case, each of these circles represent a contact, which then, so the good thing is that they can measure activity at many, many positions, and you can have many shanks, and you can have new like electrodes with like tens or hundreds or even thousands of contacts. This is based on the same technology that sort of used to make computers, so that's why it's a very advanced technology. And then we can measure things like the EEG, MEG signal, or the contribution from a piece of cortical circuit. And then you have a separate type of measurement, completely different measurement physics. You shine in light and see and measure what comes out. And then you can do all kinds of tricks, adding dyes and different variations of that to get out information about what the neural circuit is doing. And then we have two other to other like more resistance measures, where you fMRI, where you measure the blood dynamics of the brain, and then positron emission tomography, where you measure essentially the food consumption. So you have all these different measures of neural activity. But what is important to remember is that they don't measure the same thing. So just to illustrate the problem of interpretation of like experiments, we have this just sort of a foreign civilization that foreign civilization out of a non-human civilization exploring us from outer space. And then you can do, one thing you can do is sort of imaging the street lights at night. This is actually a photo that is made by adding, like, just showing how the streets are light up at night. So from this, you would sort of interpret that. So this is sort of like analogous to imaging electrical activity. From this, you would conclude that, oh, most people live in the world live in, well, Europe, and also on the east coast of the US, and Japan, and people even live in Norway. And this is not true. If you've been there, very few people live in Norway, but we are very happy with good streetlights, it seems. It's dark, and we have a lot of water power, so I guess maybe that's normal. But anyway, if you somehow measure the hemodynamic, the fMRI activity, then you would measure a very different pattern. You see, most people actually live in Asia, northern India and China. So it just illustrates that by one of these imagings alone, you wouldn't sort of, I mean, these two imaging techniques measure different kind of brain or human activity. So, and it's the same thing now if you want to sort of take advantage of all these new measurement techniques for the brain. We need to sort of make the connection between what's happening in the neuron, maybe your mathematical model for what's happening in the neuron, to what you measure. For example, if you have then this one neuron that, and they measure the spike, what you actually measure is the weighted sum of transmembrane currents in the soma region, or the potential you measure reflects that. With this other, this is the low frequency part of the potentials you measure in the brain, or E, G, and MEG, you still measure an effect of this weighted sum of the transmembrane currents, but it's like currents from all over the neuron. And if you measure optical signals, then you actually get a very different view of the neuron, because then you typically measure things from the surface, because that's closest to where the light comes in, and also closest to the detector. So that means that there's no simple relationship between these measures. So what we need to do in order to take advantage of them is to work out all these mathematical connections between the neuron dynamics and the different experimental modalities, this measurement physics. And that, I think, is something which has been done too little in the computational neuroscience. Lots of people have ideas about how information is processed, how the spikes are doing this and doing that. And this is sort of, maybe I can understand that, because it sort of is, that's where the thinking happens, right? Maybe, at least I think so, in how the spikes are processed. But in order to test your theories, you need to make this link between your model for how the information processing happens and then what you measure. And we have, in our group, have done a lot of work on how, for example, what electrical signal, the local field potential that you measure from neurons, how that depends on the properties of the neurons, where you inject things and so on. And it's not so easy to understand, or to if you don't think about it, you can easily make mistakes. For example, if you have, this is illustrated here, if you have 1 Hertz oscillatory current input into this neuron, out here up at the top, at the white dot, you get this contour line shows the electrical potential that is set up. And you can see we get this nice dipolar pattern there. The dashed and the solid line are just different signs. So you would think that if we did this 100 times faster, 100 Hertz into the top point here, you will get the same thing just 100 times faster. But you don't at all. You get something very different, which just reflects the cable properties of the neurons. And people have done mistakes in the past when interpreting this kind of data, because they have forgotten about this basic measurement physics thing. So they have all these fancy theories for power laws, this and whatever, self-organized something or whatever, where why this 100 hertz input is why typically the signal gets smaller from 100 hertz at 100 hertz and 1 hertz, which has nothing to do really with that. And what they show here is that even if the activity is the same, the spiking is at the same at these different frequencies, you will get a very different signal. So the perspective for model testing is really, if you have this candidate model here, this is what we have, this really cool model, we think, about how a piece of cortex computes, how the information flows. Then we need to make the connection between our hypothesis and all these different measurement modalities, not only spikes, but also these other measurement modalities. And then we can ask, if you have measured all these things, and now people are getting really good at measuring all these things, sort of given all this data, what sort of combination of what mathematical models agrees best with all experiments? So that is sort of like the overall workflow that I think we need to sort of pursue in order to make progress, to understand, sort of like to tune in on, or to find out, to try to find mathematical models which are sort of representative for what actual brain circuits does. So one example here is, one thing that we have just done is sort of this, we have a problem with point neurons like the integrated fire neurons, is that they don't produce extracellular potentials like LFPs. So in order to be able to compute both spikes and LFPs, we need to do this trick. So we need to, in this case, we get the spikes from this nest simulation, Potjans Diesmann model, and then we store the spikes, and then we use this multi-compartmental biophysical detail models to compute the corresponding LFP. So this was just something that was just published. This is a collaboration with people in Jülich, Potjans Diesmann and Sonja Green. But the key thing here is that we have now one mathematical model that produces both spikes and LFPs. So meaning that then we can sort of do that we can then sort of try out different network models, different parameters, and compute the same thing. And then we can compare with experiments and say, well, this is closer than this. And then this we have sort of like, learn something. So that is sort of the program. We need to sort of I think especially because we don't really understand too much about circuits yet. So I think this is a way to move forward. And this is something then we should also try to push to the also to this, not only for this measurements inside the cortical circuit or inside cortex, but also the systems level measurements. So here is sort of like in a virtual, just the illustration of what this could look like. This is like EEG, which are computed, which are generated by a model. It's a very crude model just to illustrate the principles. But that is sort of what you would like, is sort of to start with network model and hook it up and then compute all these, do the measurement physics properly, and then be able to compute the EEG, and then also in this case the fMRI that corresponds to this particular model. And this in order to do this for like a large system, we need it's like really a big infrastructure in terms of like supercomputers and programs to run it properly and so on. And this is one of the goals of the Human Brain Project, is sort of to make this possible. So that is, now I'm going to what I want to do, just mention a little bit before I close, is this. There is this other revolution, or if you call this a revolution, there's this big other biological revolution in biology that is going on, or has been going on for like a couple of decades, and that's the thing with the DNA. Right now, in 2003, they mapped out the human genome. So so that is, or we got this overall map of the human genome, 23 chromosome pairs with about 3 billion base pairs. And of course, then the first one was the first. in the beginning, it was just like 1 or 2 people who were like brain inventor, one of them, like had his DNA mapped out. But now, it's not only that it's possible, it's cheap. I mean, I had my DNA tested last year. Maybe you've done it too. I just bit into this little thing and sent it to the US. And then it was sort of cool actually. And then I came back, these interesting results that, for example, I found that I'm a lot of Finnish I'm Norwegian, but most of my DNA relatives are Finnish. So there's like a little bit sort of like something, my mother came from the extreme north, and I'm not quite sure really who, there's some kind of, I don't know. It was some kind of, but Finns are cool people, so I have no problem with that. But it's sort of interesting that I sort of, so I got this email from this one woman, she was living in Alaska, saying that, well actually I just looked into this, and then my father has like a piece of chromosome 6 identical to me, or I mean to you, which is me, and then also a piece of chromosome 13, and I inherited number 6, the part of number 6, and then my brother's number 13. So that we had something to talk about, and we talked about living in Alaska, and but it's just, what is amazing though, it's so cheap, and this was in like so now you can do this on thousands of people, right? And that is actually necessary if you want to do science, because if you want to do science with it, at least one thing you would like to do is sort of look at groups of people to see how, in what sense are your DNA, your group, different from this group, and especially with patients. And then you need a lot of patients. So one thing they wanted to do for a long time was to sort of look at schizophrenic people or patients, that how are they genetically different from healthy people. So they were able to collect DNA like analysis from like almost 35,000 schizophrenics, right? So that's a lot of schizophrenics. So this was like this international consortium, and they have 130,000 or something, 20,000 controls, and then they were able to look at statistical differences. Are there differences between on the DNA of schizophrenic people compared to healthy people? And we knew that it would be. I mean, that because it's a high heritability. And then it would be really cool if it was on like 1 or 2 places, right, on the DNA that was different, because then you could go in and fix it, change maybe that with some of these new techniques, CRISPR or what have you. But it turned out to be not like that, unfortunately. It was more like this study that came out a couple of years ago, where you actually found 108 positions along this DNA. So that was a little bit discouraging, because you can't sort of fix 108 things. And it also turned out that each of these 108 positions didn't really explain too much of the, didn't really predict too much whether you got schizophrenia or not. But then we can then go in and look at what are these 108 positions coding for. And then we got, actually when you look up in these lookup tables then we find that many of them codes for the excitability of neurons. So then what we have done and what we can do is now to explore this in the model, because in the model it's not difficult to check out many of these, many things at the same time, like, and then try to sort of fix it, fix a schizophrenic neuron into and make it healthy. So this is sort of like, I think, an important new avenue for computational neuroscience, trying to actually take advantage of all this new insight that is coming from genetic field. So this is sort of, if you sort of want to do this, because typically, as long as I've been in computational neuroscience, there's been very little interaction with the genetic community. So I think this is something which is missing, and now we start to sort of understand the link, and we can also systematically study these genetic variations of ion channels, because ion channels are proteins. So if you have DNA that is different, the protein that makes up an ion channel is slightly different, and then we can systematically look at how does that change the ion channel current and so on, and then actually get this almost like this table of elements for the different ion channels, and then also different genetic variations, which you can then put into models and explore. So that will, so the summary of key points: brain function relies on interaction across scales, and it's tough for the brain, but mankind has done it before for the weather prediction and smartphones, but they have to do things. I think we had the sociology of has been different, so I think we have to work on the sociology of neuroscience and sort of to get a better collaboration between experimentalists and modelers. This neuroscience with both hands. And the key thing then is sort of to make progress is that if you look at what the typical, if you read experimental literature on systems neuroscience, meaning that you do measurements from different parts of the brain and try to understand what it really means, then typically the typical strategy is to do measurements and then start doing statistical analysis, and then if you find something which is like statistically significant, like meaning that the p value must be small enough, and then they sort of declare victory and then publish. But it's really difficult to to make. I think that's also a lot of problem with reproducibility. It's that difficult to reproduce these studies. So maybe it's, anyway, I think it's very difficult to make significant progress going in that direction. So we need instead is to start with a model, a candidate model, which is precise and formulated mathematically, and then we use this data to falsify these different hypotheses, and then essentially formulate hypotheses in mathematics, and then compare model predictions with everything you can measure. So that's what I plan to say. So thank you.
Thank you.